So we've been talking about enolate reactivity for some time, and we now want to talk about the ways in which enolates can react with various functional groups, various electrophiles. The first class of reactions of enolates is the reaction with aldehydes and ketones. And so we want to talk about what's happening here, and the common feature of all of these reactions is that we're starting with some enolate starting material, and we're reacting it with an aldehyde or ketone. So the first reaction that we want to talk about is known as the Aldol reaction. And the Aldol reaction is a reaction in which you get a formation of a beta-hydroxy aldehyde, or beta-hydroxy carbonyl. And you get this beta-hydroxy carbonyl upon reacting an aldehyde or ketone with an enolate anion. So let's say that we started with the following aldehyde. So we have propanol. And we have propanol in excess, so I'm just going to draw in two molecules of propanol. And let's say we treat this with base hydroxide anion. So it could be sodium hydroxide, for example. Well, we know that when we treat an aldehyde with a base, the alpha protons will undergo deprotonation. So we can get deprotonation to give us an enolate in this case. Okay, and so this enolate is then going to react with the other aldehyde that we had in our starting material. And so we said that the enolate can have reactivity at oxygen or at carbon. In this case, it's going to react at carbon because that's where the bigger lobe is in the HOMO. And so we're going to attack the most electrophilic center here. And the most electrophilic center is, of course, the pi star CO. Right? So this is the LUMO that reacts with the carbon of the aldehyde, the enolate. And so the bonds that form here are going to be a new carbon-carbon bond between the enolate carbon and the formerly aldehyde carbon. And so we get an intermediate that looks like this. Right? So we get a negative charge on what was formerly the aldehyde carbon. This then is going to remove a proton from water. Right, so this alkoxy anion removes a proton from water, regenerates hydroxide base. And then we have the product, which is going to be what's known as the beta-hydroxy, in this case, aldehyde. Right, so the beta-hydroxy carbonyl in this case is the beta-hydroxy aldehyde. And so we have alpha and beta positions from that aldehyde. And so at the beta position, we have a hydroxy group. And so this is going to be the product of an aldol reaction. And so you want to think of this beta-hydroxy aldehyde functional group as derived retrosynthetically from an aldol reaction. So we can form this red bond right here through the union of an enolate, which was formerly this part of the molecule, and an aldehyde, which was formerly this part of the molecule. And so we can sort of think of this aldol reaction as happening retrosynthetically from a carbonyl, or a aldehyde or ketone in this case, or some sort of enolate. Now, the next reaction we want to talk is a variation of the first one, and that's known as the mixed aldol condensation. Okay, so this is an aldol reaction in which the two starting materials are not the same. So the two carbonyls are not the same. Now, why is this important? Well, let's consider the following reaction. So let's say we have this aldehyde, and we have this ketone. And we're going to treat this with hydroxide as base. Now, the reason why this is a variation on the first is that if we had two carbonyl species that both had enolizable protons, we could get a mixture of products. And so to overcome this, this problem, we have the mixed aldol condensation, in which one of the two products, this aldehyde here, cannot form an enolate at all. Right? So the only reactivity that this has is electrophilicity at the carbonyl carbon. Right? So this allows you to funnel into only one product. Right? So the product that's going to form from this comes from the enolate of the cyclohexanone. And so the enolate of the cyclohexanone reacts with the aldehyde of the benzaldehyde, and that's what's going to give you only one product here. So this product is, again, beta-hydroxy carbonyl, but this time it's a beta-hydroxy ketone. But this beta-hydroxy ketone, of course, has two different pieces of the molecule formed by this new carbon-carbon bond, in which those two pieces are different. And so again, we have a reaction in which we've got deprotonation of the alpha protons by hydroxide, and that's going to generate an enolate intermediate. That enolate intermediate is going to react then with the aldehyde, benzaldehyde. Right, we're going to form a new carbon-carbon bond because the carbon has the greater lobe in the HOMO. And what you get here is a new carbon-carbon bond between your carbonyl and your aldehyde. And then you simply get a deprotonation of water to give you, and I flipped it around, the new beta-hydroxy ketone as your product. Right, so the new carbon-carbon bond that forms is this one right here. Right, and again, if you're thinking of this retrosynthetically, this comes from an aldol reaction. Right? Okay, now this can happen again, and so if we have two equivalents of the aldehyde with respect to the ketone, we can get another deprotonation to occur with hydroxide, but it can occur on the other side. Right, so we get a new enolate to form, and so we've got now our beta-hydroxy ketone is going to be a beta-hydroxy enolate, which then reacts again with the aldehyde. And I'll just say if two equivalents. You can get another reaction between the enolate and that carbonyl carbon to give you a new beta-hydroxy beta-alkoxy ketone. And then that, of course, does a deprotonation of water to give you the dimer. And so we have here a ketone with two beta-hydroxy groups on either side. Okay, so alpha beta in this direction and alpha and beta in this direction. Both forms coming from the new carbon-carbon bond here that derives from this central enolate and either the blue aldehyde piece or the red aldehyde piece. So retrosynthetically thinking of this in terms of an aldol disconnection. Now, the reason this mixed aldol works is because, only one enolate can form. So the enolate can only form from the cyclohexanone. It cannot form from the benzaldehyde since it does not have any alpha protons. But 2, the aldehyde is actually more reactive than the ketone. So even if you had this enolate here, you're only going to react with the aldehyde as the electrophilic partner. You could potentially react with the ketone, another cyclohexanone, but we know that ketones are less reactive, slightly higher pi stars than aldehydes are, and so we can only get it to react with the aldehyde. Now, this beta-hydroxy carbonyl function group is very unstable, and in most cases, it will eliminate water to give an aldol condensation product. And when using ketones and aromatic aldehydes as substrates, this is actually known as the Schmidt reaction, the product of which is a chalcone. And so let's talk about the Claisen-Schmidt reaction. Okay, so the Claisen-Schmidt reaction is an aldol condensation reaction between a ketone and an aryl aldehyde. But it requires a little bit more forcing conditions. And so what normally this means is you're going to have probably excess base and a little bit of heat. Okay, so let's say we have this aryl aldehyde. Let's just say it's a 3-pyridyl aldehyde. And we're going to react it with this fancy ketone. Now again, don't lose the forest for the trees, right? This is just a ketone with some alpha protons and an aldehyde, which is electrophilic. And so when we react this now, we're going to use 10% sodium hydroxide, so pretty high concentration of sodium hydroxide. What we're going to get is an elimination product, or aldol condensation product, in which we've got this species here. Right, and so we have an alpha-beta unsaturated carbonyl as our product. All right, so how does this work? Well, we probably need to go through the intermediacy of an aldol reaction product. And so let's take our sodium hydroxide and let's deprotonate the only spot that we can deprotonate, which is the alpha proton from this ketone. And so we're going to remove that proton to generate an enolate. That enolate is then going to react with our 3-pyridyl aldehyde, and it's only going to react at the more electrophilic aldehyde carbon. And so we get the electrons to move down. The carbon of the enolate is the one that reacts, and that's going to give us a new carbon-carbon bond with an alkoxy group, beta to that system. Right, so our new carbon-carbon bond is this blue bond right here. Now what happens next, of course, is we get a deprotonation of water to give us the aldol product. So let's just draw that in. Now it's at this point, remember, when we're under excess base, we can get another deprotonation to occur. Right, so we can have an enolate form once again. And when that enolate forms, you form something that looks like this. And then what will happen is that you can form product directly by doing a mechanism known as an E1CB. And E1CB stands for elimination first order conjugate base. So we can kind of think of this intermediate here as having negative charge. It's the conjugate base of the deprotonation, right? The acid that is the ketone. And so what can happen is you can move the electrons down, the pi bond moves over and eliminates hydroxy anion at the same time. And so this reaction is under thermodynamic control. And it's under thermodynamic control because now you have a conjugated alpha-beta unsaturated carbonyl. Right? The last step of this mechanism is known as an E1CB, right? And so the CB, obviously stands for conjugate base, and it's the rate-limiting step of this reaction. So it's the rate-determining step. So if you're thinking of this alpha-beta unsaturated carbonyl as in terms of retrosynthesis, this alpha-beta unsaturated carbonyl comes from the Aldol reaction followed by an E1CB mechanism. And so in order to do that, you need an Aldol condensation reaction between a ketone and an aldehyde under forcing conditions. Talk about another reaction. The last reaction we want to talk about is the Mukiyama Aldol reaction. Now, this aldol reaction involves a little bit different of an intermediate. All right, so this intermediate involves an enolate-like intermediate, which you've seen before, and that's the silyl-enol ether. Okay, so the silyl-enol ether. Okay, so let's think about this in terms of a failed reaction first, and so I'm going to draw a reaction that is not going to work, and we'll then propose a way to solve this, and obviously the way to solve this is the Mukiyama Aldol reaction. So here's the problem. The problem is that if you have a ketone and an aldehyde, and you treat it with, let's say, LDA, you're going to get a mixture of products. Okay, so the first thing that could happen is you could maybe deprotonate the aldehyde. And so you get an aldehyde here that's been deprotonated. This enolate can then react with either another equivalent of the aldehyde, or it could even react probably in small amounts with the ketone. Okay, so we already have two different products that could form. And those are, of course, going to deprotonate with water to give us the beta-hydroxy carbonyls. And so we've got one product here, two products here. We could also do the same thing with the ketone. We could undergo deprotonation to give us this enolate. Now this enolate can, of course, react with the aldehyde or ketone. And you get what's known as scrambling. Okay, so we've got several different products that could form from this reaction. So we react with H2O again to undergo the deprotonation. To give us beta hydroxycarbonyl and another beta hydroxycarbonyl. And so this is product 3 and 4. And so because we have 4 different products, we've got a problem. We have no way of controlling this, and say this reaction is scrambled. Now we could avoid this, and we could avoid the formation of these 4 different products by doing a Mukiyama Aldol reaction. And so the solution to this is that form the silylenol ether of this species. So let's take this ketone, let's make the silylenol ether. So if we recall how to do that, we take TMS chloride, which acts as a Lewis acid, binds to the carbonyl, and then that allows then deprotonation alpha to the carbonyl to give you the silylenol ether functional group. And so we do this with the ketone, the one that we want to have as our nucleophile. Right? So this is the thing that has the enolate-like reactivity. This is the silylenol ether. And so we're going to use this carbon as the more delta minus carbon, and that's going to have the enolate-like reactivity. So we're going to take that reaction, take that reagent, and we're going to react it in the first step with our aldehyde in the presence of titanium tetrachloride. And then we're going to work it up with ammonium chloride. And then the product that we're going to get is the aldol product, in which we this beta hydroxy carbonyl, beta hydroxy ketone in this case. So how does this work? Well, the first thing that happens is that the titanium tetrachloride is going to coordinate to the carbonyl. So we kind of have the lone pairs on oxygen bind to the titanium, and that's going to give us a really electrophilic species. And that species is so electrophilic that it's going to react with our silylenol ether. And so our silylenol ether, the electrons on oxygen move down, the carbon attacks the carbonyl, electrons move up onto oxygen. And so now we have our new carbon-carbon bond to form. We still have a bond at TMS, so oxygen's positive. So again, our new carbon-carbon bond is this blue one right here. And then, of course, we can simply just use ammonium chloride as a proton source in a workup step, and that's going to protonate off the oxygen-titanium bond to give us the beta hydroxy carbonyl compound as our product. So this is a Mukiyama Aldol reaction. We can control which kind of aldol product that we get by using the intermediacy of the silylenol ether. So we first form the silylenol ether in a separate flask, then we take that silylenol ether and in the second reaction flask perform the Mukiyama Aldol reaction, in which we already have control over which species is nucleophilic. Other types of Lewis acids that work in this reaction, besides titanium tetrachloride, are things like BF3. It has a empty atomic p orbital, of course, on boron, but also things like metal salts, zinc chloride, and magnesium chloride. And so those are the reactions of enolates with aldehydes and ketones.